Zoom session is being brought to you by the Fractal Bullseye Fire. Okay, for today we'll be doing exponential functions and exponentials base e. An exponential function is of the form f of x equals a to the power x. A is called the base, x is called the exponent, therefore the name. Here's an example, 2 to the x. For values of x, we get these values of 2 to the x, an eighth, a quarter, a half, 1, 2, 4, 8, an eighth, a quarter, a half, 1, 2, 4, 8. It starts up very small and zips to becoming very, very big. That's for base 2. Now, various bases will give you different shapes with certain similarities. So here's a graph of 2 to the x. Here's a graph of 3 to the x. Here's a graph of 1.5 to the x. 1 to the x is a constant 1. 2/3 of the x is falling, the way 1.5 to the x is rising. 1.5 is 3/2, 2/3 x, 2/3 is reciprocal. These are flips of each other. 2 to the x and a half to the x are flips of each other. 3 to the x and 1/3 to the x are flips of each other. Page 2, graphs. Okay. If a, the base, is bigger than 1, you get what's called an exponential explosion, starting small and ending very big. If a is between 0 and 1, then you get what's called an exponential decay, starting big and ending small. All these go to the point 0 by 1 because a to the 0 is always 1. 1 to the x is 1, it's a constant. And a to the negative x is 1 over a to the x. So here we have 2/3 to the x and 3/2 to the x flipping each other. A half to the x and 2 to the x as flips of each other. A third to the x and 3 to the x as flips of each other. Now, there are various uses of the exponential. One of the most common that you really need to know about is compound interest. If you don't know about compound interest and how exponentials can grow very quickly, very fast, then watch out. The credit card companies will eat you up. I mean this. But okay, so if we have P is the principal value of an account or a debt or whatever, and A is the final or later value of the account, R is the annual interest rate, K is the number of compoundings per year, so quarterly K is 4, monthly K is 12, daily K is 365, and so on, and T is the time in years. Then A equals P times 1 plus R over K to the power KT. So we have some examples. 5 to the x, graph it. Well, 5 is bigger than 1, so it starts small, goes through 0 by 1, and ends very big. A quarter of the x, well, a quarter is between 0 and 1, so it starts big, goes through 0 by 1, and ends small. Here, 3 to the x minus 2, we have the exponential explosion 3 to the x, and we lower it by 2 units. So it goes, for example, through 0 by -1, and it has a leftward asymptote of -2. Negative of 2 to the x, well, 2 to the x starts small and ends big. This minus flips it up for down, so it starts small and ends big negative. Here we have a principal of 10,000 growing for 10 years, compounded quarterly at a rate of 8% per year. What's the amount? Well, here we go. P times 1 plus R over K to the KT. P is $10,000. R is 0.08, rate 8% is 0.08. Where K is 4, KT is 4 times 10. So it's 10,000 times 1.02 to the 40, which after a bit of calculation is $22,080.40. It's slightly more than doubles in those 10 years. How much more interest would $10,000 earn in 5 years, compounded quarterly at 5.5% interest than at 5% interest? All right, so we calculate the interest of the amount at 5%. 10,000 times 1 plus 0.05 over 4 to the 4 times 5 is 1,282.04 cents. At 5.5%, the later amount is 10,000 times 1 plus 0.055 over 4 to the 4 times 5, which is $1,314.07. The difference is $32.03. Okay, that suffices for that.